let's give you a quick review for previous class. We talk about the fluid chemical reaction. Okay, so fluid chemical reaction can be a gas react with liquid or two insoluble liquids. So the purpose here, by using the fluid reaction, can be production of your desired product between the two soluble liquid or the gas react with liquid, and probably can be separate a constitute from a fluid. So this can be used to remove gas from a liquid mixture. Okay, so what's the fluid chemical reaction? What's the overall reaction process? So we have a gas A react with liquid B and generate product R, and in between the gas and liquid, we have a film layer formed in between the gas and the liquid. And on the left-hand side, nearby the gas phase, we call it a gas film. And on your right-hand side, near the liquid phase, we call it a liquid film. But overall thickness, we call it a film layer. And here is the interface between the gas and the liquid phase. So because this is a gas, so in order to plot the concentration and content of gas A, we use the partial pressure. So molecule gas A into the gas film will diffuse through the gas film, and you can see that the partial pressure of PA decrease as function of location. As long as molecule A dissolve in the liquid phase, then you can get, based on the solubility of gas A dissolved in the liquid phase, we get the Ca prime or Cai as the interface, and molecule A will diffuse through the liquid film to reach the liquid B. Okay, and regarding to the solubility of gas A, you can use this equation as long as you know the Henry's constant, and also you know the partial pressure at the interface, then you can get the Cai concentration of A at interface. Okay? Before we quantitatively get the consumption rate or formulate the rate equation for fluid reaction, you need to know some assumptions. The first one is we assume this kind of heterogeneous chemical reactions belongs to second order reaction, and the rate equation can express like the consumption rate of reactant A equals to rate constant times Ca and Cb. And based on the solubility relationship, as long as you know the Henry's constant, then you know how much gas A can be dissolved in the liquid phase. And the other thing is most important is liquid B is not going to enter the gas phase. So no reaction happens in gas phase, included gas film. And all reactions only happen in liquid phase, included the liquid film and bulk liquid or liquid main body. So we try to enlarge this region. You can find the gas A and liquid B. In between, we got the film layer. And as you know, when you try to plot the concentration profile, as a function of location, you can get the PA and diffuse through the gas film. And based on the solubility, you got the Cai, and also A is diffused through the liquid film and react with B. Okay. So in the fluid-fluid reaction, when you try to formulate the rate equation, always express in the unit of what? Foprong. Foprong means the consumption rate of reactant A per reaction volume. In this case, the reaction volume is the gas volume plus the liquid volume. We call the reaction volume. And some people probably will express like the consumption rate of reactant A per liquid volume. And this is the upper interfacial area. But based on consumption rate of reactant A, you can get this equation here. And also finally, we can get four prong. R4 prong can be expressed like FLRAL equals ARA double prong. So as long as you know the RAL means the consumption rate of reactant A in liquid volume per liquid volume, you can simply times the FL and you can get the R4 prong. If you have the flux R double prong A is per interfacial area, you can simply times the A, then you can dot the R, you can get the 4 R4 prong. So normally we will use the consumption rate of reactant per reaction volume to describe the fluid-fluid reaction, to describe the rate equation of fluid-fluid reaction. And next, we are going to try to formulate the equation or results for the rate equation for fluid-fluid reaction based on the concept we learned is the electrical circuit concept. The concept of the electrical circuit and finding the driving force, total resistance, and the flux passing through resistance. So this is the results we are going to demonstrate and show you how to obtain this relationship or the rate equation for fluid-fluid chemical reaction by finding out the driving force and total resistance. And this is the 4 prong. Don't forget, it's per reaction volume. So we are going to spend 2 slides to derive that results, show you how to derive that results to you. But simply, we will divide it into 2 parts. The first part is, yes, you know the driving force, but the resistance, the A diffuses through mass transport through the film layer and reaction with B. So you can consider as a series reaction included mass transport in film layers and reactions with bulk liquid. So we divided into these 2 processes. The first one is only mass transport, straight mass transport of reactant in film layer, included the gas film and liquid film. No chemical reactions in film layer, only mass transport. And next will be, we assume the transport is very fast and only reaction in bulk liquid. So we are going to sum up these results and to get the rate equation for fluid-fluid reaction. So first of all, how to get the consumption rate of reactant A per reaction volume in this straight mass transfer case of reactant. There's no chemical reaction, just mass transport. So we try to plot the concentration as a function of location. This is gas A, this is a bulk liquid, and in between we get a film layer, gas film and liquid film. As we know, the A, as long as A molecule enter the gas film, the concentration will decrease as a function of location, and we get a PAI, is a partial pressure of A at interface. Based on the solubility of A dissolved into the liquid phase, we got a CAI. So as long as we know the Henry's constant, we can get a CAI. As long as after A entering the liquid feed also obey or diffuse through the liquid feed and arrive the bulk liquid, and we got the concentration Ca. As long as it reaches steady state, you can expect the flux passing through gas feed will be equals to the flux of A passing through liquid feed, and only all these belongs to mass transport, only mass transport. So for the flux passing through gas feed, we can easily write down the flux, double prime is a flux, right? And transport coefficient KAG and PA minus PAI, and KAG is a diffusivity of molecular A through the gas feed divided by the thickness of this gas feed. Okay, this is a KAG. And as you know, this is per interfacial area per unit area, right? It's a per area. But as we mentioned before, for fluid-to-fluid chemical reaction, we want to express this as a 4' is a per reaction volume. So we can just times the A for this equation and get this 4' and KAGA PA minus PAI. And regarding to the flux passing through JA passing through liquid feed, we can RA double prime KAL transport coefficient of gas A or A molecular diffuse through liquid feed, and CAI minus CA converted to per reaction volume with times A and get these results. And next is, as long as this reaches steady state, this flux should be equals to this flux. And the following calculations was based on what? It's very difficult to measure the, no matter it's CAI or PAI at the interface between gas and liquid. So the purpose is to delete the PAI or CAI. So how to do that? So we want to move the KAGA to the left-handed side. So we will get this term KAG and this one PA minus PAI. And as you know, what's a PAI? It's a HACAI, right? And the second equation, you just move this to the left-handed side and you got the 4' A, KALA and CAI minus CA. In order to delete this term, we want to use this one plus HA times this equation. Okay, so we can drop this term out, and after arrangement, we can get this results. This result is consumption rate of reactant A per reaction volume equals to PA minus HACA divided by these terms. So this is quite similar with what we learned before, right? Learned in the fluid-solid reaction is the flux, but this is just per reaction volume. It's a per reaction volume. Consumption rate of reactant A per reaction volume. Driving force. So what's this driving force? We express in pressure. So PA minus this, we need to find the difference in pressure, right? Ca is the concentration. In order to find the difference and the unit will be pressure, so we use PA minus HACA. So the upper portion will be, the unit will be pressure. So serving a driving force. And the bottom part is the total resistance. And as we learn in fluid-solid reaction, the transport resistance is a reciprocal of transport coefficient. Reciprocal of transport coefficient in gas feed. But here we still have A. We times A because in fluid-solid reaction we use the double prong, right? It's a flux, right? But here we want to convert it to the photon is a per reaction volume. We need to times A. So this is A. So we put the A to modify that. This is a transport resistance in gas feed, and also this term is a transport coefficient in liquid feed, and it expresses reciprocal of KALA. Yes, it's the same, right? But you find, oh, here is HA. Why, Professor? Why there's a HA here? Because the upper portion we express this in unit of pressure. But here, as we know, the unit to describe the content in liquid should be a concentration, right? So we divided, so here HACl, so we divided, we put HA here to divide it with this one, so we got the concentration here. So this is, we got the driving force is pressure difference, and total resistance is resistance here, transport resistance in gas feed and transport resistance in liquid feed, and we express this and this is reasonable. Okay, so this is only mass transport in thin layer, no reaction. Next, we consider is a reaction in bulk liquid and no mass transport resistance. No resistance means transport is very fast. So that tells you the concentration remain constant in gas phase, gas feed, and also in liquid feed. Concentration remain constant. And so based on this, you also can write the equation here is a consumption rate per reaction volume. This is what we are interested in. Can be equals with what? Total consumed in chemical reaction. So it's a consumption rate of reactant A per liquid volume. And this one should be equal this one. So you got this times this equals to this times this. And you move this to here. So you got the RALFL is a ratio of V liquid volume divided by reaction volume. Basically, you can get that, right? So what's the RAL? Consumption rate of reactant A per liquid volume. So this is what you learn in rate equation. For this one, actually, we assume in previous slide, we assume page 14 something. We assume it is a second order reaction. So you can write the RAL KCACB. So we substitute this into here. So RA for prom will be KCACBF. Easy, right? So you just arrange it. So CA becomes to PA over HA. And the rest of part you put here. So you can consider the bottom part as a reaction resistance. So now you have what? You have mass transport reaction. So you sum the results you derived in previous two slides. We can rewrite this equation is flux, but this flux you can consider is a per reaction volume. Consumption of reactant A per reaction volume. Driving force is a partial pressure of gas A, and total resistance included the transport resistance, transport in gas feed, transport in liquid feed, and reaction resistance in bulk liquid. It turns out is a universal and beautiful results, right? To describe the rate equation of fluid-fluid chemical reaction. But there's something missing. What? Based on the previous two slides, mass transport here, reaction here, so you got these results. But on page 14, we mentioned that very important image or maybe information is, how about if the chemical reaction can only happen in the liquid phase, including liquid feed and bulk liquid, but the results we derive here we assume there's no chemical reaction happen in liquid film, only mass transport here, and chemical reaction. So this beautiful equation or results cannot deal with if you have a chemical reaction happen in liquid film. That's not good, right? Because you get the results, but this results cannot deal with if you have a chemical reaction happen in liquid film. It's not good. So we need to do some modification on these results by introducing you a very important term or parameter we call E is the what is the liquid film enhancement factor in the film layer, and we'll put the E here. So the modified term E here help you to what? Tell you that liquid film, as after you ended the E, this modification term, then this term can cover if less transport and also a chemical reaction simultaneously happen in this liquid film layer. So that now this E included the transport resistance and also the reaction resistance. It's a very interesting term I introduced to you. And the definition, we are going to show you the detailed definition in following slides. This is E. And liquid film enhancement factor is to describe how much chemical reaction, how much A be consumed for chemical reactions in the film layer. And also, besides the E, liquid film enhancement factor, we also want to introduce you the other very famous term we call a Hantan modulus, MH, to you. And based on the definition, is a square root of conversion rate, is a chemical reaction rate, and divided by the transport rate in the film layer. So based on the definition, you know, as long as you have a higher, larger Hantan modulus, that means in this film layer, we have what? We have the chemical reaction faster. We got the instantaneous, a very fast chemical reaction rate compared to mass transport. Why this Hantan modulus is so important? Because when you determine whether you have a chemical reaction happen in the liquid film or in the bulk liquid or both, is based on what? Based on you compare reaction rate and the mass transport, which one is larger, right? If you have a reaction rate is very fast, transport is slow. For example, like if now you plot the A, right? Reaction transport is very slow, and reaction is very fast. So as long as B enter here meet with A molecule, then they will react simultaneously and very fast react, right? So in this kind of case, if the reaction is very faster than mass transport, then chemical reaction can probably will happen in liquid film only. But if the mass transport is very fast, then chemical reaction is very slow. So probably most of the chemical reaction happen in bulk liquid. So actually the value for MH is play a very important key parameter to determine whether your case is one of the parameter to determine whether where the chemical reaction happens. And E is also very important because it describes how much A be consumed for chemical reaction in this liquid film layer. Okay. So let's move to the detailed introduction of E and liquid film enhancement factor and the Hantan modulus. So let's introduce the E first. I just copy these results to here, and we want to explain more about the E is a liquid film enhancement factor. We try to, because everything is described in the liquid film layer, so we try to enlarge this liquid film layer and use this to describe the flux of reactant A. Okay, so in this liquid film layer, if we want to try to write down the concentration gradient or profile in this liquid film layer, we know that the molecule A will diffuse through this liquid film layer by mass diffusion and is through mass transport, right? So as long as we fix the concentration gradient at the two ends of this liquid film layer, then the flux is fixed. So the flux is fixed for mass transport in the liquid film layer. But if there are chemical reaction happen in the liquid film layer, that means what? In liquid film, we need to consume more reactant A for chemical reaction. So that will and this flux remain constant, and you need to spend more A for chemical reaction. So the total flux here need to increase. So this is a full story. So what's the E? Based on definition is the rate of take up of A when reaction occurs, divided by the rate of take up of A for straight mass transport. It means the mass transport only. So this you can consider the flux when you have a chemical reaction happen. So the flux included the mass transport and chemical reaction. And this is the flux only for mass transport. So you can expect it. If we don't have a chemical reaction here, so the flux should be the same. So E equals to 1. So we have the bottom limit value for E is equals to 1. But however, if the chemical reaction happens, they will consume extra A, so the flux will increase. So E will increase in the meantime. If the chemical reaction happens very fast in the liquid film, so E will get larger and larger. And everything is we describe is in the liquid film. So the value for E, definitely, as long as you have chemical reaction happen in liquid film, E must larger than 1. And let's check. If E is larger, then total resistance will decrease. Resistance decrease tell you the flux will increase. So that will consume more A, right? It's reasonable. So it turns out it, based on the physical meaning, it turns out works. And yes, you know the bottom limit value for E, but how about if E, whether E has a upper limit value? Yes, because it definitely for any chemical reaction, you have limited A, right? So in the instantaneous reaction, that means if we have an instantaneous reaction, that means that this reaction is very fast, instantaneous reaction, because the rate, so that happens very, very fast. Then E has an upper limit. We call it EI. I is instantaneous, the abbreviation for instantaneous reaction. Okay? So this is a physical meaning and some concept about E. Okay? And this slide, it says now you know the E, right? So next slide, we are going to show you several different types or kinds of fluid-to-fluid reaction based on what? Based on different reaction rates and also the low concentration of Cb and high concentration of Cb. And this is actually we have 8 different types of cases involved in fluid-to-fluid chemical reaction. But the purpose here is we want to show you this uniform results, this results rate equation to describe the fluid-to-fluid reaction. This results works and can be applied for any cases we discuss here. Okay? And here, as we mentioned, this is an instantaneous chemical reaction compared to mass transport in the liquid film. This is instantaneous reaction happening in liquid film. Then this is a faster reaction, means not as fast as instantaneous, but a little bit slowed down. And this intermediate means a slower than faster reaction. And slow reaction means very slow. So very slow means what? Mass transport is fast. Okay, this is important. And also I remark some, in this textbook, you remark something is for instantaneous reaction and fast reaction, you can observe that reaction only happens in liquid film. So reaction only happen in liquid film no matter it's a low CB or high CB cases. You can observe all chemical reaction only happens in liquid film. No reaction happen in bulk liquid. So that means the A don't have chance, molecular A don't have chance to enter the bulk liquid. It will be consumed completely in the liquid film. But in the case in intermediate reaction, that means the chemical reaction slow down. Then A have chance to enter the bulk liquid. That tell you for intermediate reaction, no matter it's low CB or high CB, chemical reaction included will happen included film layer, liquid film layer, and bulk liquid. So it's in liquid film layer and bulk liquid. And for the slow reaction one, slow reaction, chemical reaction tell you that the transport is very fast. So in this case, no chemical reaction happen in liquid film. All reaction happen in bulk liquid. So in this case, you know this E equals to 1. Okay? Okay, so let's give you more detail about these different cases. For instantaneous chemical reaction, that means reaction happen very fast. So when you try to plot the concentration profile of reactant A, you can observe molecular A enter the gas film, the concentration will decrease as a function of time. And based on the PA equals to HACA, as long as you know the Henry's constant, you can know the Ca, right? And A also diffuses through the liquid film. And at this time, B, bulk liquid, also will diffuse through the liquid film. As long as A met with B, and reaction very fast, so you can get the reaction plan. Here, we have a reaction plan due to it is an instantaneous chemical reaction. Some people probably will have questions. Ca is larger than Pa. CAI is larger than PI. No. The vertical acid, the unit for vertical acid is different. Here is the partial pressure. The unit is partial pressure. But for this one is the concentration it's in concentration. So the axis is different. The unit of axis is vertical axis is different. So as I mentioned, PA, as long as you know HA, you can calculate the CA. Okay? And here is a low CB case. How about if we increasing the concentration of CB to high CB, then you are going to push this reaction plan to where? To here is the interface between gas and liquid. We also have a reaction plan. So in instantaneous reaction, chemical reaction is a plan and only happen in liquid film. And how about if we the reaction slow down to fast reaction? So because it's fast means the A met B, then they will react to generate product, but it's not as fast as instantaneous reaction. So you can observe instead of reaction plan, you get a reaction zone here at low CB case. When you increase the concentration to high CB, then you will get a reaction zone. You will see that the reaction zone will be pushed to the interface between the phase gas and liquid. Why this is the B? Because B is not have chance. B cannot enter the gas phase. So this is the only possible reaction plan happen at the interface between gas and liquid. So no matter it's instantaneous reaction or fast reaction, all the chemical reaction only happen in liquid film layer. No chemical reaction happen in the bulk liquid. So you can see that the concentration profile of Ca don't have chance to enter the bulk liquid region. So reaction only happen in liquid film. But how about if we slower down the reaction to intermediate chemical reaction? So that will result what? Reaction gets slower, so you can find that the Ca enter in the bulk liquid. So the reaction will included liquid film layer and bulk liquid. So this is liquid film layer and bulk liquid. And based on this, there's one thing I need to mention that some higher Cb, if Cb is high enough, then B is just spend tiny amount of B to react with A. So the profile here, sometimes if Cb is high enough, so the profile here can consider as remain constant at of the Cb remain constant. So negligible. I mean this remain constant because B you just need to spend tiny amount of B to react with A as long as you have high enough Cb value of Cb. And how about if we have a slowest reaction, chemical reaction, that implying what? Mass transfer is quite fast. So mass transfer very fast and reaction, right? So all the chemical reaction happen in bulk liquid. So based on this, you know E equals to 1 because no chemical reaction happen in liquid film. So you got the rate for mass, and you got E equals to 1 in this case. Okay. So we already introduced you several different types of cases of fluid chemical reaction by different reaction rate and different concentration of Cb. So next we are going to show you step by step for case by case to confirm whether this case, when you try to write down the consumption rate, rate equation, when you try to derive the rate equation, can we directly use this modified results to confirm whether after serious deviation will you get these results? So if yes, then you can directly use these results to answer or to obtain the rate equation for fluid reaction, no matter what kind of cases you're dealing with, right? Okay, so let's move to the first one is instantaneous reaction. Instantaneous reaction, this is low Cb, this is high Cb cases. As we mentioned, we have reactant A, Pa, diffused through the gas film, so you can observe the partial pressure decrease as a function of time, and based on solubility you got a CAI, and also A diffused through the liquid film react with B diffused through the liquid film, right? And they will react, so you can observe the concentration will drop to 0 for both A and B molecules because it's instantaneous. So you also have a reaction plan, and when it reach steady state, you can formulate the equation about the flux, right? Because 1A will react with B of B, B mole also B. 1 mole of A will react with B moles of B. So based on flux, you know JA over JB will be what? B times JA equals to JB, right? B times JA equals to JB. You got this equation, right? That's this plan. And when you try to increase the CB, then because you increase the CB, so the gradient increase, so flux will increase. So the plane is going to, because flux increase, so the plane is going to be pushed toward the left-handed side to reach the interface of gas and liquid. and to establish a new equilibrium conditions. And in this case, what is the rate limited step for this kind of heterogeneous fluid-fluid chemical reaction? You can check these figures. A will diffuse through gas fin, right, and directly react with B, and this is very fast. So the rate limited step will be only one. It's based on the A diffuse through the gas fin. So it's the mass transport in gas fin will be the rate limited step for instantaneous reaction at high CB case. In order to quantitatively to demonstrate the results the modified results we derive from previous slide can be performed for each case. So we want to derive to get the consumption rate of reactant A per reaction volume. To show you, you can perform this on this case. Okay? So let's show you how to derive and get the consumption rate of reactant A per reaction volume. This is a figure we want to plot. It's a low CB case, and PA and PA decrease to PAI to reach the interface between the gas and liquid. And based on the solubility, we got the CAI, and also A diffused through the liquid fin and will react with B completely. So you can observe the concentration for A and B will drop to 0. And the thickness of this liquid film layer is x0. And the left-handed side belongs to left-handed side we call it x. And right-handed side here is x0 minus x. We got the thickness here. Okay, so as long as it reaches steady state, we can formulate the JA and JB, right? So JA actually, A is passing through flux it's a flow through gas fin and liquid fin. So flux of A in gas fin will be flux transport coefficient times PA minus PAI. The same, right? And A, flux A passing through liquid film, so it's diffusivity concentration gradient. So CAI minus 0 divided the thickness x. And flux of JB will be what? Diffusivity dBl, concentration gradient, thickness divided by thickness, x0 minus x, you got the thickness. And as we know, you can, what's the DAL? DAL, you want to convert it to transport coefficient, can be DAL divided by x0, the thickness of liquid film, you got the KAL. So you got KAL times x0 equals to DAL. And also, what's the DBL? You can get the DBL transport coefficient KBL equals to diffusivity divided by thickness x0. So DBL can be expressed as KBL times x0. And as we know the relationship between JA and JB, right? Why? Because 1 mole of A react with B moles of B. So you know the B times JA equals to JB. So we use this left-handed side and right-handed side here. So we got this result. So you can check KAL, CAI, x0 over x. Yes, left-handed side. Here, KBL, CB, x0 over x0 minus x and over b. Yes. So we got this equation. And we move from this term to a left-handed side. And after arrangement, we got this results. And here, we need to deal with the CAI because, as we mentioned, CAI is very difficult to measure the concentration of A at the interface. So what information we have here is, yes, you got CAI here, right? So CAI equals to PAI over divided by HA. So you can, after arrangement, you can get PAI over H times x0 over x, and you also have Henry's constant here and consumption rate, and over the KAL, you got these results. And here is very important because this term, if you divide it by HA, then you got the identical results here. So these results can be expressed like this, equals to this, right? So now we focus on this equation. We want to delete CAI, so what information we have is these results. We converted this partial pressure in express of Ca, concentration, divided by HA. So you sum this equation up, then you can directly drop the CAI term, and after arrangement, you got this result. Consumption rate of reactant A per unit area expressed like this. And here, in order to simplify this situation, we make a very important assumption. We will assume there's no gas phase resistance. That means transport in gas phase is very fast. So PA equals to PAI, and CAI equals to CA. Okay? And you can directly drop this term out, and you only have this term times to the upper portion. Then you get this one. So we successfully get the flux JA, consumption of reactant A per unit area, expressed like this. And what is this term? Actually, this is EI, is a liquid film enhancement factor at instantaneous reaction or at infinitely fast reaction. But how? Why? In order to persuade you this equals to EI, so let's check the page 32. E, based on definition, is a total consumption rate for mass transport and reaction, and divided by mass transport, right? So diffusivity concentration gradient plus reaction consumption rate. So you need to diffusivity concentration gradient divided by B. This is for A, right? You divide it by B, so this is A reaction. A for mass transport, A for reaction. So after arrangement, you got this result. This result is identical with what we learned, right? So that is EI. It's a maximum value for E. Because we already consume most of A for reaction, this is the maximum A we can provide it. Okay, so this is EI. The same, right? So put EI here, and after arrangement, because this is double prong, we want to convert it to 4 prong. Sorry. So times the A to this equation, and after arrangement, we got the CAI, and bottom part is here. So this is after checking this one, you know, no reaction happen in bulk liquid, no transport resistance in gas phase. So the only one we have for resistance is a liquid phase resistance here. This is we successfully get the rate equation for instantaneous reaction at low CB case. But this is, yes, we did that, right? But we need, the second purpose here is to confirm whether these results can, this unit for modified results can be used, can be performed for this case, right? So let's check. Here is an instantaneous reaction, so no chemical reaction happen in bulk liquid. You drop this term out, so no resistance. And we also assume there's no gas phase resistance, so this is small. So this is what we have, right? For liquid phase resistance, PA over HA is CA, right? And the rest of part is the same, right? Because CA equals to CAI, right? And also here EI, so yes, you need to put here. So the E, for instantaneous reaction E, you need to use EI. And EI, how can you get the EI? Yes, EI equals to this. You just put the CB, CA, and B, and DBL and DAL. You know the EI for your interesting reactions. So this modified results can be performed for instantaneous reaction at low CB case. How about high CB? High CB, when we try to increase the concentration of CB, then we push the reaction plan to the interface of gas and liquid. And now what we need to concern is the rate limited step would be the transport in the gas feed. So when this is a rate limited step, so we try to write down the flux. So KAG PA minus minus PA0, or PAI equals to 0, so PA minus 0, and this is the transport coefficient. And we also want to convert this double prong to 4 prong times the A together. After arrangement, we got these results. Let's check whether we can use these modified results. For instantaneous reaction, no resistance in bulk liquid, no reaction resistance in bulk liquid. And in this case, A don't have chance to enter the liquid film, right? So no liquid resistance for liquid film. And only one we have is resistance, transport resistance in the gas film. So identical, right? So we can successfully confirm that yes, we can use these modified results on the instantaneous reaction at high CB case. Okay, so this is a short summary here. For instantaneous reaction, no chemical reaction happen in bulk liquid. You directly drop the reaction resistance here. And for low CB case, we assume there's no transport resistance. So drop this term out. So we can successfully get the consumption rate per reaction volume expressed like this. And don't forget, this should be put EI here. And for the high CB cases, because we push the reaction plan to the interface of gas and liquid, then only we need to consider for rate equation will be the transport in gas feed. So, and A don't have chance into the liquid feed, so we don't have the resistance for liquid feed. So only thing we have is a transport resistance in the gas feed. So we successfully write down the rate equation here for the high CB case. Next, we are going to show you is the fast reaction in liquid film. Fast reaction means that the reaction is not as fast as instantaneous reaction. Slow down, so you got the reaction zone. Instead of reaction plane, you got the reaction zone here. So for the low CB case, you got the reaction zone in the liquid film. When you increase the concentration of CB to high CB, as long as CB is high enough, so you can consider the concentration of CB remain constant. So some people will call this situation as a pseudo first order reaction with respect to A. Why people call it that? So we will explain that in this slide. For low CB case, for this case, because yes, we don't have chemical reaction happen in bulk liquid, so we drop this term out and we just copy the rest of part here. So we can successfully to get the consumption rate per reaction volume by what, as long as we know the E. So the important part here is you need to define or obtain the E, then you can get the RA for pro. This is for low CB case. And for high CB case, because CB is high enough, so you can consider the concentration of CB remain constant in the liquid film. So based on this, when you write down the rate equation, consumption rate of reactant A KCACB, because CB can consider as a constant, so you can lump K and CB to become K prime and CA. So you find that consumption rate of RA is proportional to CA and it's a first order. So in this case, people also call it the pseudo first order rate equation with respect to CA. In this situation, you also need to define what is E, right? And people tell you that, and textbook tell you that under this situation, E equals to Hantel modulus. So as long as we know the Hantel modulus, you input the Hantel modulus to substitute E, you can write down the RA for pro. So now we are going to show you what's the Hantel modulus. Page 32. Based on the definition of Hantel modulus, is everything is happening in the film layer. Maxima possible conversion rate divided maxima diffusion transport rate through the film. So based on this, we need to write down the conversion rate, the chemical reaction rate, so it's KCACB times the volume. And then you can get the total number here is you can get the conversion rate. And here you got the what? You got the diffusivity concentration gradient, and this is flux, so you times the area. And based on this, you drop this term out and drop this term out, and after multiply, you got the KCB x0 divided by KAL. X0 equals to DAL over KAL. So you got the Hantel modulus square becomes here. You take the square root of it, so you got what I told you. So Hantel modulus, so it becomes here. So as long as you know the concentration of CB, you perform your experiments at constant temperature, and dA KLB remain constant, then you know the MH, right? And you substitute E with MH, then you can get the RA full pro. Yes, it turns out perfect. But professor, you haven't talked about how to get the E or obtain the E at the low CB case. How to do that? Let's move to simulation results here on page 31st. This is a simulation, a numerical solution or simulation published in 1954. And if you take a look on this figure, is the E liquid film enhancement factor as a function of MH. MH is Hantel modulus, as I mentioned, is the reaction rate in film layer divided by transport rate in film layer. So with increasing MH means what? In the film layer, the chemical reaction is happen faster than mass transport. So based on this concept, you find there's a different regime and expressed in different color based on instantaneous. Yes, you got the higher MH, right? Faster reaction, and faster reaction at high CB case. This is a fast reaction at low CB case, and this is a fast reaction at high CB case. So with increasing MH, you can observe what? You can observe means the reaction happens fast in the film layer compared to mass transport, right? So you can get instantaneous and fast reaction. Okay, and how to use this results to get the E for fast reaction. Fast reaction is a yellow region. How to do that? You can observe there's several curves, 2, 5, and 10. This is the EI. The value for EI is E liquid film enhancement factor at instantaneous reaction. As long as you know as long as you confirm what kind of chemical reaction you're dealing with and you define the concentration of CB, then you can have you can know the curves belongs to your reaction. For example, if you input all the parameters here, including CB and PAI, then you got the EI equals to 2. Then that tell you what? That tell you in your cases, as long as you fix the concentration of reactant A and B, then you got the maximum value for E, right? And under this case, you need then next you need to calculate the value for MH in your cases. So as long as if you find the MH is like a 1, 2, 3, 4, 5, it's 5, then you can extract or get the value for E by using this figure. So if we got the EI equals to 2 and MH equals to 5, then I can get the value for E. As long as I know the E, then I can put it back into and I can get the RA formula. Right? For example, like if you input all the conditions and you got the EI equals to 5, then your behavior will obey these curves, right? And after calculation, you know the MH equals to 10, then, and this belongs to fast reaction at low CB case, then you need to know, as long as I know the E, then I can complete the RA formula, right? So E can be read out here. Dun, 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 dun. So based on this concept, if I know the CB, PAI, and all everything, and EI is equals to 5, right? Can I convert it? Can I change my reaction from fast to instantaneous reaction? Yes. The only thing you need to do probably is you can try to increase the value for MH. Then you can tuning your chemical reaction from fast chemical reaction to instantaneous reaction. Okay? And the other thing is regarding to the fast reaction at high CB case, it belongs to pseudo first, right? And based on the description in previous slide, we know the E is equals to MH. It also based on this simulation result. You see, this green is pseudo first, so E equals to 100 and MH equals to. So it's the same, right? And when MH equals to 1000, then we confirm E equals to 1000. Okay? The other thing is, some people probably will ask, Professor, the question is I don't know how to determine whether my interesting reactions belongs to instantaneous, fast at low CB, or fast at low CB or fast at high CB. It belongs to pseudo first. How to do that? How to know that? Based on this simulation, they also provide you extra information regarding to help you to define whether your experiments belongs to instantaneous reaction by compare EI and MH. If EI is smaller than MH divided by 5, then your reaction belongs to instantaneous reaction. And for instantaneous reaction, you need to know, as long as you know the EI, then you can complete the rate equation RA formula, right? Because E equals to EI. And if your MH is in between 5 EI and EI over 5, then your reaction belongs to fast reaction. In that fast reaction at low CB, so in that case, you need to read out the value for E by using this plot. And if your EI is larger than 5 mH, then your reaction belongs to pseudo first. So E, you just directly input with mH, and you can get the RA formula. So this is how you determine whether your interesting reactions belongs to what kind of chemical reaction belongs to instantaneous, fast, at low CB, or pseudo first. Okay, so today we ended here.